power and replicability, some basic statistical concepts. Generally, small signals and small effects are not good for business. We are talking about the scientific business generally. This is not a statistics course, but back in class 1.6, when we introduced fMRI, we talked about the concept of a statistical effect too. In biomedical sciences in general, because we are often dealing with noisy data, we often need to make use of statistics. Sometimes this is just unavoidable. People are just different. Even within a person, the brain does not react to the same stimulus the same way over many repetitions. So a statistically significant effect is just a difference or some pattern in the measurement that we can observe relative to the variability or the noise of the data. When we say an effect is statistically significant, we mean that the observed pattern of the data is rather unlikely to be just noise. When we say the p-value is smaller than 0.05, what we roughly mean is that, had there not been any real pattern in the data, and all is just noise, the chance of us seeing something like what we see here would be smaller than 5%. So it is very unlikely that the results are due to chance. Very likely the results are meaningful. This is usually the criterion by which we report the effect as positive. So the statistics, when done right, are meant to make sure that our positive results are not fluff. But what happens when we have a negative result? That is, a null result. Well, that's trickier. In general, when you don't see something, you can never be sure it is not there, or that you don't see it from the right angle. It may be because our measurements are too noisy, or that they are not the right kind of measurements. Sometimes there's just no way to tell. But let's say we have the right kind of measurements. That is, if there is an effect, it should show up in what we are measuring. Now, there is still the issue of how big the effect is supposed to be. If we expect a big effect, and if we can see that the data is not all noisy when the data fails to show the pattern we expect, we can say, okay, probably the effect isn't really there. If it were there, it should show up clearly relative to the noise. Then we can interpret the null result accordingly. But when we expect a very tiny effect in the first place, when the statistics don't turn out positive, we are in a tricky situation. It would be very difficult to tell, is the effect there but just masked by all that noise? Or is it not there at all? In general, we say that to detect small effects, we need more data. In neuroscience experiments where we study a group of subjects, the higher the number of subjects, the more we are able to detect smaller effects. Sometimes we denote number of subjects as n, so n equals 10 means that we have 10 subjects. Another way to put it is to say as we increase n, we tend to have higher statistical power. Power is the probability of being able to find a true effect if it is there. So it is a somewhat symmetrical concept to p-values. Recall, that is roughly the probability that we call something a true effect, when actually the underlying data is just fluff. So power depends on how many subjects we have, as well as how much data we collect per subject. The more subjects we test, the more power we have. Power also depends on the size of the effect we expect. If the effect is big, obviously we expect to have a higher chance of being able to see it, given the same number of subjects. Now comes the really bad news. In cognitive neuroscience, traditionally, up till recently, our power is poor. We say most studies are underpowered. This may be somewhat okay for the positive results we have found. When our p-values are small, in principle, the effects are still likely to be true. But this is a real problem for the null results we report. This is one of the important reasons why some people say there is a replication crisis. That is, many studies don't replicate. This may reflect many problems in the way experiments are done, but one of the reasons is we don't have enough power. So even if the effect is there, we may not see them replicate. When power is low, we don't expect even true positive findings to replicate. Now then, some effects may actually be fluff too. In that case, Even if we have enough power, we may not replicate them. So we need to find out which studies incorrectly reported positive results. But when we don't have enough power, this whole problem just becomes much worse. We just don't know what to make of null results. Fortunately, the field is starting to correct itself. It's not all so bleak. We can estimate how much power we need to make sure we test enough subjects, and people are increasingly doing that. Also, in science, single studies are often not so decisive anyway. We try to document everything and see how things converge over the long run. Overall, many findings do converge. But meanwhile, this remains a particularly bad problem for small effects. For them, when we get a null result, it is really very difficult to know what to say.